Okay, now we're on the question 7, sub-questions A and B, and on exercise set 4. So let's look at this question 7. Now it is a chi-square test question. As I said before in the videos and on the theoretical lecture videos, we use these two tests called Magro-Rosmino test and chi-square test to understand if this sample random number sequence fit to the uniformity property, if it conforms the property of uniformity. Now, okay, we have a sample size of 50 and numbers between 0 and 1, 50 random numbers, and it says choose 5 number, not 5 numbers, I'm sorry, choose n equals 5 and implement the chi-square test for a significance level of 0.05, and it's as if the sample is uniformly distributed. And on question B, it's as use Microsoft Excel and the chi-square test to check if the random numbers generated by linear congruential method. Okay, for the sub-question A, let's start. Okay, for the chi-square test, we have a sufficiently long random number sequence, and the chi-square test divides unit interval into n intervals. So chi-square test divides the unit interval into n intervals of so they should be equal length, right? So n intervals with equal length. So a proper choice of n would be between square root of capital N, which is a sample size, and n over 5. And the chi-square test uses the test statistic formula sigma j 1 to n oj minus ej. I will explain these ej. So this oj here, as you can memorize from O, is the number of observed random numbers in the jth interval. Observed number of observed random numbers in the jth interval. I am fast forwarding because I have to solve the question, okay? This is the expected number of observation in the jth interval. So go and watch the lecture videos if you didn't before watching this, a reminder. Okay, where this AJ, oh, what AJ is EJ, okay? I can't believe I said that. Okay, it's EJ is the expected number of observations in the jth interval, and it equals to capital N over N. So if the sequence of random numbers from R1 to Rn is truly uniform, the test statistic follows the chi-square distribution with V equals n minus 1 degrees of freedom. Okay, let's write V equals n minus 1 degrees of freedom. So we have an algorithm of the chi-square that has an algorithm. We choose an n value such that it conforms to this interval. It's between these. We calculate the test statistic, which is given with this formula, and we find this critical value we have found in the second step in the table, chi-square distribution for our degrees of freedom, n minus 1, and our significance level alpha. If this critical value is less than our test statistic, we reject the null hypothesis. So fun. Okay. So if we reject null hypothesis, it says that the random number sample does not follow the uniform distribution. This question took so long. Oh. I'm just gonna write otherwise. Okay, we say that there is no evidence to reject null hypothesis if the test statistic is less than or equal to the critical value. So the random number sample may come from a standard uniform distribution. Again, we have to write the what's happening. Okay. Where this and this is otherwise. Okay. Finally, let's start the question. Okay, we have these numbers. What was okay? It was 7. Now we will be constructing a table for the chi-square test for n equals 5 intervals. So since it is constructed for 5 intervals, we can divide 1 by 1.0 by 5 and find these intervals. These intervals are of equal length. Now these are kind of my bins. We have J here. So just like we did in the common girls may note that this is like the iteration. Now we have the observed value, expected value, And to implement the formula, we have to find the OJ minus EJ. And find the square of this. And after calculating the square of this, OJ minus EJ, we have to divide it by EJ. Okay. So we have to actually look at the given data on the paper for question 7. If it falls in between 0 and 0.2, we have to count the number of numbers that falls into this interval and write it. Okay, so if you count accordingly with relevant to these intervals, for example, 0.07 falls in the interval of 0.0 and 0.2, right? So how many numbers between that? We are finding those and writing. So expected value is actually found here, right? At the beginning of this topic, I remember you have seen the for the standard informed distribution, like how many values, how many the expected number is n divided by n. So this is our sample size, and n is the number of intervals. So if I have 100, what was this? Okay. 5 intervals. Where is the question? Okay, it's 50, not 100. That's why I got confused. It's okay. So it's 50. 50 divided by 5 is 10. So I expect 10 here. What is the notation of EJ is we said the expected number of observations in the jth interval. So in the first interval, second, third, fourth, and fifth interval, I expect 10 number of observations. However, these are my observed numbers. Okay. So OJ minus EJ, 10 minus 6, I mean, no, 6 minus 6 minus 10 is minus 4, minus 1, and 6, 2, and minus 3, right? So we have to take the square of them. 16, 1, 36, 4, and 9, and divided by EJ. So what's the EJ here? 10. So 16 divided by 10 is 1.6. 1 divided by 10 is 0.1. 36 divided by 10 is 3.6. This is 0.4, and this is 0.9. Okay. So in the formula, we have to sum these up, right? Let's sum these. Okay, this is 13, 14, 20, 26, 4, 6. I think it's 6.6. Yeah, So our test statistic is equals to 6.6. And our degree of freedom is, so what was the degree of freedom is n minus 1. N is 5, the lowercase letter n. So it is 4. And our significance level is 0.05. We look at the table for the degree of freedom 4 and the significance level of 0.05 and find the critical value. Okay, so the test statistic is 6.6 and the critical value is 9.49. And what we said here is that if so this conforms to the results, right? Yes. So if the test statistic is less than or equal to the critical value, we fail to reject the null hypothesis. Our null hypothesis was this random sample is following a uniform distribution, standard uniform distribution. And if you fail to reject that, we say that it actually may can come from a standard uniform distribution, this sample. Okay, let's say that. Since and we can write that the sample may have uniform distribution. Okay, now I will be switching to Excel. So I will stop the recording and continue to record now. Okay, now we're on Excel and question 7B. It says use Microsoft Excel and the chi-square test to check if the random numbers generated by linear congruential method generate capital N. 500 random numbers using linear congruential method with parameters A, okay, I think I was not in this question. No, okay, it's true. Implement the chi-square test and calculate the test statistic for n equals 20 for significance level of 0.1. Conclude if the sample is really uniformly distributed or not. Now we're on 7B. Okay. So these were the numbers from here, right? Not here. We did these here. On question 5, we have computed these numbers using this multiplier, increment, modular, and seed number, which is given in the question 7 as well. It asks us to generate random numbers 500 random numbers using linear congruential method, which we did in the fifth question. So it was, oh my God, it was 10,000 numbers, but now it's accessed 500. Okay. After creating this, just like we did in the fifth question, these are our random numbers. So at first we computed xi's and our i's were computed, as you remember, I over n, like we did here, I over m. Okay. Now, the questions asked implement the chi-square test and calculate the test statistic for n equals 20, blah, blah, blah. Okay. Now, we have this J1 to 20 are number of breaks, and because it's asked for n equals 20 in the question. Okay. Now, these are our breaks. If we divide, 100 by 20, you get these breaks. And so naturally, these are our bins. And just like we did in the sub-question A, this is our observed number of data between the values between 0 and 0.05. So these are my numbers. If I have, obviously, so apparently, we have 23 observations of these values and between 0 and 0.5. So you can find this number with sum if method or frequency method. Okay, this is my observation column. This is my expectation. So this expectation is just like we did in the sub-question A. It is found by, so my capital N is 500, N is 20, right? So it is 25. The expected value is expected number of, observation is 25, but the realized is this column, in this column. So we compute this, OJ minus EJ. If you double click on that, it is a formula and you propagate it down. And we take the square of this. If you click it again, it's a very short formula, so you don't have to type in like a square or something. And then I didn't do it. Okay. Well, then we divide this value by EJ. So EJ is the expected number in the intervals. Okay. So our sum is just like we did on the iPad when I was drawing. We are summing this up because the formulation goes like this: the OJ minus EJ square divided by EJ, and we are summing these up over J. So if you sum these up, we get 11.44. So so when we look at what is the question we're asking us, so what did we find earlier was that X, okay, that's right, like the test stack was, let me check what was that. Okay. But this is very okay. I'm sorry. It is very distinct from here because we have 500 here and it was a different question. Okay, we we actually found the test statistic here. If we sum these values up, it's 11.44, which is our test statistic. Let's write this. And okay, our critical value. Okay, our alpha not alpha is significant level. It is, what was it? Okay, 0.05. So we check the table, chi-square table accordingly. And if you do not know how to check the table, you can ask, or I can show you. We can show you in the recitation. So the critical value with this, and I almost forgot the degree of freedom. The degree of freedom is n minus 1 is 19. So if you check up, it is 36. Okay, so since this critical value is greater than the test statistic, we again fail to reject the null hypothesis. So this sample may come from a uniform distribution. And do not forget, at first you are writing the null hypothesis. What is the null hypothesis? And alternative hypothesis, which is I follow a uniform distribution. And this is otherwise does not. Okay, this was the end of the question 7, I guess. Let's stop.